Okay, now we're going to kick it up a notch and go beyond a few select point polarization states, purely polarized incident and detected polarization states, and ask what happens in another very common architecture where we've got a linearly polarized input, but we're varying the orientation axis of the incident polarization, and then measuring the horizontally polarized second harmonic generation and the vertically polarized second harmonic generation as a function of this incident polarization state. And it makes more sense to vary the incident polarization state in this way than putting a half wave plate on the detection arm, for example, because you have a quadratic dependence on the incident polarization state and a linear dependence on the detected. And one easy way to do this polarization rotation, for example, and the most common, is probably just by using a half wave plate. So this would be, for example, if we have a half wave plate for the fundamental beam and we want to know how we can connect the intensity of these two polarization components back to the local frame and Jones frame in this observable architecture. So the polarization state, this is the general expression for the Jones vector for the second harmonic as a function of the driving electric field and the Jones vector. And of course, the Jones vector, the vectorized form of the Jones tensor is what we want to pull out of this analysis. And all the elements inside this matrix E are the inputs that are known. This is the known incident polarization state. So if we just substitute this expression for the incident polarization state, then let's just consider, for example, either the H or the V, just one of the two polarization components in this Jones vector for the doubled frequency. Then it's pretty straightforward to convince yourself that you're just doing a Kronecker product of these two terms. And if we just explicitly evaluate and multiply out all of those terms, and you end up with this expression for the n-polarized doubled amplitude, the amplitude of the electric field for n-polarized light, as a function of this polarization rotation angle gamma. And of course, if we're measuring the intensity, then we're detecting the squared magnitude of that response. And what does that look like? It looks kind of like this. Just keep on multiplying things out, and then we can group terms. And if we take advantage of the fact that that we're doing second harmonic generation, then there's some degeneracies such that NVH and NHV are equal. And that leads to some of these factors of 2 and 4 that show up in here. And I'm not going to go through the details of where this expression came from, but it's really just straight multiplication of these three terms with themselves, and then grouping terms grouping everything in terms of the common dependencies on gamma. And so we can write this out. What the beauty of doing it this way, in terms of this framing, is that you learn that you have a total of 5 observables in this experimental architecture. There's really 5 measurements you can pull out because there's 5 components, 5 dependencies, angle dependencies on gamma that relate the intensity back to the Jones tensor. And that's a good thing because we really only have 3 unknowns, because we're talking about n-polarized light. We have 3 unique elements for horizontal and 3 unique elements for vertical. And we have 5 observables for horizontally polarized light and 5 observables for vertically polarized light. So it's an overdetermined system, which means we can come up with unique values, as long as we're talking about real valued tensor elements. If they're complex valued, then things get a bit more interesting. But in general, in second harmonic generation, you're either probing things that are far from resonance, in which case you can expect the tensor elements to be real valued, or you're probing things where everything is very close to one strong resonance, in which case, again, everything is not real valued, but likely to be of identical phase, and so therefore these same assumptions hold. All right, so how do we pull it out experimentally? Actually, before I get there, all right. Let's just ask what happens if we do have complex valued tensor elements, because it'll turn out to be useful later on. And it's just a slight deviation. Instead of having this be squared, it's the squared magnitude. And instead of having this be the product, it's the real part of the complex conjugate of one multiplied by the other. So nothing really dramatically different if we allow this to be complex valued for the tensor elements, except for the fact that we have doubled the number of unknowns, because we have an amplitude and phase for each of the tensor elements, but we still only have 5 observables with 6 now unknowns. We can get around this by referencing the phase relative to one tensor element. And that way, the other two tensor elements, the phase shift relative to some reference tensor element, brings us back to 5 parameters and 5 unknowns, such that the system can be uniquely determined. I won't go into too much detail on that, again, because in microscopy, it's not all that common to have complex valued tensor elements to contend with. All right, so how do we then take advantage of the fact that we know something more about the local frame response? And there's symmetry there. For example, in a membrane interface or in collagen, we know that we have either 3 or 4 unique tensor elements, depending on how important this chi XYZ is. And I'm just looking, for example, I'm just doing an illustration of the most common and simplified case in which collagen, for example, is oriented within the focal plane, and it's just azimuthally rotated some angle, and we can use this matrix to connect this rotation matrix multiplied by all the other good stuff to get from Cartesian to Jones. If we multiply that out, then this term goes away, and we have an 8 by 3. How do we take advantage of the fact that we have 3 elements here, but 8 here, or 6? I'm sorry, 6, because we're doing second harmonic generation. How do we take advantage of this local frame symmetry? And the answer is that there's no simple, great way to do it except brute force. So we know, and the reason it's a challenge, we can't do a simple linear inversion like we could before, because all of these scale non-linearly with the tensor elements. So we have a quadratic dependence between the elements in the Jones tensor and the coefficients, these A through E polynomial coefficients. So there is no way to linearly invert that because of this nonlinear quadratic scaling. What we can do, however, is just a general brute force approach where we define chi squared. And this is not to be confused with chi 2. Chi squared is simply the sum of the squared deviations between what we measure, and that's A measured, and what we predict those A coefficients should look like for a given set of guess values for the local frame tensor elements. And then we just brute force minimize the value of chi squared with respect to each of these individual guess values for the effective local frame tensor elements, with all of the things being known. And what we, as soon as chi squared is minimized, then those are the most probable values for the local frame tensor elements based on those sets of observables. And then we can also recover the uncertainty in each individual. For example, chi YYZ, then I would be YYZ, and the uncertainty, the variance in that is just given by the variance of the fit S squared multiplied by the alpha inverse, where alpha is defined as this matrix of second derivatives of chi squared with respect to the individual tensor elements that you're fitting. Let's just ask one more question. Let's say we kick it up one more notch and throw in a wave plate after the sample, or throw in a reflective interface that we don't want to have there but is there and we have to deal with. How do we handle the fact that there might be some post-sample polarization dependent optics that could influence and introduce crosstalk between the tensor elements that we detect? I'm not going to go through the derivation of this. It's actually pretty straightforward, although the equations look kind of nasty. We again have 10 observables we can collect, 5 for each polarization dependent detector, the horizontal and vertically polarized detectors. And each of these has a summation within it, and the summation is actually pretty straight. It's only 2 terms in the summation, for M is horizontal and M is vertical. And then we know that we have some Jones matrix, and we can describe all of whatever happens after the sample and between the sample and the detector by one complex value Jones matrix. And as long as we know that in advance, and there's easy ways to make measurements of that based on linear optical interactions and Jones manipulations, as long as we know M, then we know the contributions of chi HH and chi VHH to the measurements for AH and AV. And it's just, there's a little bit of each in there because potentially, depending on what M looks like. And again, from that point on, we can just do the same brute force approach for calculating the most probable values of the local frame tensor elements from these A through E polynomial coefficients, the set of 10. along with their corresponding uncertainties.